pleasure to be here. Thank you for inviting me back.
We're happy to have you. She was here in person, and that was awesome. But this one is
I'll do that
so
again.
close.
I promise. I mean, now that COVID is done, I mean, you know, I mean, I think I was in California at first, and now I'm just in Washington. So it's not so hard to get to where you guys are.
Yeah, it's only what, 5 hours?
Yeah, yeah.
Yeah, okay, cool. So I'm going to show some pictures from the James Webb, and you're going to tell us a little secret about each one, perhaps?
I certainly will. And also, I'm really looking forward to taking people's questions. So you questions about the James Webb Telescope itself, or questions about the images you see, or you know, I should mention anything you'd like. You know, even if it has nothing to do with the James Webb Space Telescope, feel free to ask your question. I'll answer it as best I can.
Oh, wonderful. Well, I guess we're all going to think of a question as soon as I get to the right page. Hold on. You know, I spent 100 hours on this PowerPoint, and we're not going to see it all. But that's life. Okay. Wait a minute. I don't want that one. There we go. Can you see that?
I can't see the image that you're showing because I think maybe you're not sharing your screen, but just tell me which one it is and I'll be fine.
Okay, this is Stefan's Quintet. I've got a picture from the Hubble on one side and an image from the Webb on the other side.
That's right. So Stefan's Quintet is a famous group of galaxies.
Jeremy?
Actually, of the 5 galaxies, four of them are close to each other, and one of them has just kind of gotten in the way of the picture. It's actually a little bit closer to us. But the wonderful thing about those 4 interacting galaxies, so galaxies get bigger by smaller galaxies coming together to form bigger galaxies. You know, one of the things that we've found out through Hubble and now through Webb is that the farther away you look out into the universe, you know, that of course means the farther back in time you're seeing, because light travels very fast. It travels at 186,000 miles per second. But even at that speed, if something is very, very far away, it can take billions of years to get to us. And so when we look back in time, many billions of years, we see lots and lots of tiny little galaxies. And, you know, it's easy to say the word galaxy, but I think a lot of people don't understand how big these things are. So like take the Milky Way, which is a nice big, as we say, spiral galaxy. How big is the Milky Way? So the sun is huge. You could fit 1 million Earths inside the sun. That's how big the sun is, just one of the stars. So how big is the Milky Way compared to the sun? So if you made the sun the size of the dot of an I on a page of text, so just like take out a book, look at the dot of an I. So if you could fit 1 million Earths in the dot of an I, then our galaxy, the Milky Way, would be about twice the size of the Earth. So galaxies are huge. They're collections of hundreds of billions of stars. And there are 4 galaxies in this image that are actually coming together. Gravity is bringing them together. And you may have heard that the universe is expanding and all the galaxies are moving away from each other. And that's true for pretty much everywhere. But the galaxies that are very close together and the gravity is strong still come together and actually form bigger new galaxies, kind of merge together if they're close enough for the gravity to actually be stronger than that expansion of space. And so these are galaxies coming together, and with the especially with the Webb image, what you see is the underlying structure of the galaxy, not just the starlight, but where all the dust and gas is and what it's doing and how the dust and gas is being mixed up as these galaxies get ready to come together. And in one of the galaxies, it's one of the one that's on the top left hand of the image. It has a very, very bright center. And the reason it's so bright, both in visible light and in infrared light, the type of light that Webb sees, is that there's a giant black hole in there, a black hole that is many, many millions of times the mass of our sun. And that big black hole, as these galaxies are coming together, a lot of gas is actually getting fed down that black hole. And so black holes themselves emit no light at all. They absorb every type of light there is. But there's so much hot gas cramming itself close to the black hole that it just lights up the galaxy. It's really, really, really bright. So that's the Stefan's Quintet image. And it's a famous cluster of galaxies. It actually appeared in the movie It's a Wonderful Life. You know, with Jimmy Stewart, you know, all the way back in the 1940s. There's a scene, it must have been one of the first images from the Palomar telescope, where they show you this quintet of galaxies. So it's an old favorite of ours.
Michele, I want to apologize to everybody, but The picture of Stefan's quintet is so little on our screen because we're sharing it with too many places. So hang on a second. We're going to get our boss to stretch that out. I need an IT man. There he is.
So somebody give you that big, beautiful image we took. We want you to see it really large.
Okay. Okay, right now
That image right there.
Yeah, the problem is, okay, so.
We were sharing and
That's Drew there, right? Hi, Drew.
There he is.
Michele,
We got it big, yay.
And give me a second.
Sometimes he just has to walk into the room, and it's all better.
Sometimes.
I'm the same way. Computers never like me, and then I'll call an IT person, and they just basically say,
Can we
"Hi,
put a
Michelle,"
face in?
and then the computer starts working. So.
Yay, that's better.
So let me,
So it's in Pegasus, and I was showing you the picture of the same quintet from the Hubble, and I don't want you to trash the Hubble, please. It's been a beautiful source of information for 30 years, so bravo to Hubble, but it won't last a whole lot longer.
Well, remember that they're just different types of lights. I mean, the amazing thing about Webb is it sees in this invisible type of light that we don't see. So the Hubble image of Stefan's quintet
That's
is
perfect.
gorgeous. And that's the visible light image. That's what you would see with cameras that were sensitive to the same type of light that our eyes are. But Webb is sensitive to a lower energy light that we don't detect called infrared. And normally we think of this as heat light. Anything that's warm, that has a temperature, actually glows bright like a star when you look at infrared light. So for astronomers, the really big deal about that with these galaxies is we don't just see the stars. We see all the material between the stars that isn't glowing in visible light, but it's giving off warmth and heat, and it's showing you how this merger is taking place. Does that make sense?
I especially like the top one. Let me see if I can point to it right here. It's been told in your group that you had on Tuesday when we did the big reveal.
Uh-huh.
Did you watch it, the big reveal on Tuesday morning?
Oh,
Some of
yes,
us did.
yes.
They said that top galaxy is definitely a black hole.
Exactly. So the middle, like I was saying, the top galaxy, that really, really bright part of the middle, that is gas that is millions of degrees hot, and it's going down almost like water down a drain down the black hole. It's getting really hot as it spins faster and faster around the black hole. Awesome. And this is one of the big goals of the Webb telescope, is that we have found out that galaxies, all have these big black holes in the center. And the crazy thing is that even when we look very far back in time, we look at galaxies as they were, say, 13 billion years ago. They already have these big black holes in the center. So is that how a galaxy forms? Do these big black holes form early in the universe and then stars collect around them? That's one of the big questions the Webb is going to try to answer, is how do galaxies start forming, and how do these giant black holes help that? Wow. And so, I mean, right now you are orbiting a black hole. Very cool. You're going around the black hole at the middle of our galaxy at 500,000 miles an hour. So the black hole in the middle of the Milky Way is about 25,000 light years away from us. And 1 light year is about 6 trillion miles. So it's definitely far away, but we are orbiting it. The sun and the entire solar system is orbiting around it at 500,000 miles an hour right now. So, that's our big, massive black hole. And it looks like, pretty much every galaxy has one too. And we're definitely going to be studying that with Webb.
Okay, let's try another picture, okay? Let's see
right.
if Tish can do it.
Then you got to tell me which one's your favorite.
Uh-huh. He said I could click this. I'm not clicking. It's clicking. Not working. Should I
Drew.
click that way or this way? You got my Pegasus moving.
Yep, that means it's active, but we gotta get back to it.
What? Oh,
Try it now.
okay.
Still nothing.
Am I doing it right?
Did anybody out there actually watch the live broadcast on Tuesday when we unveiled the images?
Yay! I've got some hands.
Did people? Yes?
No, we didn't get to the next page. It's not going anywhere.
I have to tell you, that was really hard. There were all kinds of technical difficulties.
There we go.
Hey, now we go to Canada. And
Can you see this?
Oh.
Michelle, can you see this?
I can't see it, but all you need to do is tell me which one it is. And
The
I know
Carina
it very
Nebula.
well. This is the Carina Nebula?
Carina Nebula, yeah.
All right. Okay. Carina Nebula. So Carina Nebula is actually my favorite thing to view through a small telescope. Whenever, you know, I mean, a lot of you out there are amateur astronomers. Oh, there we go. Now I can see it. Yes, yes, because now you're sharing your screen. Yay.
Maybe forever.
Okay.
Don't go anywhere.
So just so you know, these are both images of the Carina Nebula, one from Hubble and one from James Webb. They're not images of the same part of the nebula. So don't try to match them up, one for one. So the visible light Hubble one is from a different part of the nebula than we were able to photograph.
Different part of the nebula. Okay.
The nebula is a huge cloud, trillions and trillions of miles across, of dust and gas. And inside there are hundreds of young stars forming. And I mean, even like I said, the Hubble image isn't of the same part of the nebula, but if you look at the Hubble image, the smaller image, what you can see is all the dust. And you can see this beautiful shapes of these weird kind of lava lamp shapes of all the dust. That's dust that's forming stars, but the stars are forming inside. And it's a little bit hard to tell, but with the Webb image, you can still see a lot of dust, but you can see all of these stars inside the nebula that we couldn't see. In this one image, there are hundreds of stars that we couldn't see before. And one of the big advantages of infrared light, why we launched an infrared telescope, is it's really good at seeing through dust and smoke and that kind of stuff. You know, a lot of people know that fire departments use infrared cameras. And I mean, yes, infrared cameras are sensitive to heat, and that's great. But the thing that they really use them for is to find people that are, say, passed out in a room full of smoke that they can't see anything in. With infrared cameras, you can see right through the smoke, and you can see where everything is and where everybody is. So we're using that same effect to look into the nebula and to actually look into the dust so we can see where the stars and planets are forming. So this nebula is full of so many amazing shapes and weird squiggles of dust. I mean, all of these are gigantic. The tiniest little bumps you see are much, much bigger than our solar system. And actually, the visible light image we even call the Mystic Mountain because it's shaped like this wonderful, huge mountain shape. That's all being sculpted by stars that are born, and then they turn on, and there's all this heat and all this radiation. And they're actually winds of high-energy particles that come off the stars, and they start to blow the nebula away. And as they blow the nebula away, the denser areas that are forming stars kind of hold together, and they form weird shapes as all the dust is blown around them. So that's what you're looking at. You're looking at many, many hundreds of new stars being born. And this was one of the big goals of Webb, was being able to look through that dust and see where the baby stars, baby planetary systems are. And we're seeing that. And the thing that I have to really emphasize for every single one of these images, I wish I could say this in huge, big capital letters. These were all quickly taken. People wanted data quickly. They wanted to know the telescope was working. There was political pressure, make sure you release images quickly. And a lot of times these Hubble images took days, weeks, or even months to make. And we were able to do them with James Webb in a couple of hours. So we will show you more of the Carina Nebula. We will do a bigger scan of the Carina Nebula over time. This is just our first image of it. There will be many, many more to come.
Should I push the other button? Which button do I push? That one? Okay.
But it's like I was saying, if anybody watched that live broadcast, that was really hard because we kept trying to get like Canada to do something and then they dropped out. So that was one of the tougher things I've ever done. But hopefully it didn't look.
See, everything doesn't go perfectly for NASA either.
Oh Lord, no! Especially when it comes to like trying to get video
But
feeds.
she
from
was bouncing
overseas.
around the world on Tuesday and trying to talk to everybody. I'm just trying to get 3 people together. Okay, so we're doing all right here, Drew. We see 2 images from 2 different
Ring.
infrared telescope parts.
Oh yeah.
And I also put in the constellation that it's in.
That's right. Yes. So this is the Southern Ring Nebula. Absolutely
Southern Ring.
beautiful, beautiful nebula. So Tish, do you know what kind of nebula this is? What's going on here?
It's a planetary nebula, right?
Yes. And what does that
I got
mean?
one. Okay. And what else? Oh, what does it
They're
mean?
beautiful.
It's not a planet. but it looks like one.
It's one of the worst names thing in astronomy because people named it before we knew what it was. So they saw all this hot glowing gas around some stars. They said, hey, maybe that's what forms planets. Maybe planets form out of all this hot glowing gas. No, this is actually the other side of star lives. This is a star death. So with the Carina Nebula, we saw all these stars forming inside this big cloud. This is now a single star system that is dying. And there were two stars. There were a binary star, two stars orbiting around each other. One of them was about the mass of the sun, a little bit more. And after it lived for some billions of years, its nuclear reaction stopped. And a lot of you have heard that when the sun dies, it'll bloat up and become what we call a red giant star, get very, very big, and then it will begin to die. And when these stars die, they just unravel back into space. They bloat up and get really big, and then eventually those outer layers just keep on going. They just keep distributing themselves back out into the galaxy. And then with them, they bring all the stuff that makes us up. I mean, this is where we find things like carbon. We're made of a lot of carbon, water molecules, oxygen molecules. This is the process that actually forms those. And so you're watching a dying star here unraveling back into space. And there are two stars, as I mentioned, and we'd never been able to actually see both of them at once because one was so much brighter than the other. And in the near infrared image that you see, that's the one on the left. Near infrared is a type of light, very much like red light. It's just a bit more red than our eye sees. It's just off the end of our visible spectrum. And what I love about this is that normally with Hubble, you would just see that hot interior region right around the star. Here we see all this beautiful orange and red gas that's spiraling off the star. It's still moving very fast. It's moving at millions of miles an hour, but it's drifting away back into space. But in the mid-infrared image, the one on the right, that's an image in mid-infrared at a longer wavelength, a lower energy, and it's more sensitive to heat, to the temperature of things. And there you really see there are two stars in the middle. And the thing that I love this is because the reason you don't see that other little star, usually both in visible light and even in near infrared, is it's tiny. It's a dead core of a star. The star died, the nuclear reaction stopped, all the layers unraveled away, and there's the core of the star left over that's only about the size of the Earth. It's tiny. It's something called a white dwarf star. So remember I said that 1 million Earths could fit inside the sun? So someday the sun will unravel like this, and there'll just be the dead little core left, just cooling off. It's not generating any more energy, just cooling off. And that's will be about the size of the Earth. And it's not very bright in visible light or even near infrared because it's so small. It's a little thing, the size of a planet, a small planet. But it's putting off so much heat. This is the core of the star exposed. It's about 100,000 degrees on its surface. And in the image that's more sensitive to heat, you can actually see it. It's actually putting out so much heat, you can even see it next to its companion star. So, this is a beautiful example of a dying star. This is actually what I studied. This was what I did when I was an astrophysics researcher, was I studied the winds of these dying stars and how they create these beautiful clouds as the star unravels back into space.
Marvelous.
So a lovely image. We've done star birth with Carina and now star death with the Southern Ring Nebula.
And we want you to know that when you download these pictures, they're always free from NASA, and you should definitely zoom in on the background stars and see how far you can go, because sometimes you can zoom and it's all fuzzy, but these are clear for a long time. So
they're
try
beautiful to
zooming
zoom in.
Okay, let's go to another one.
All of our data is going to be free to the public. Absolutely. Yeah.
All right.
Yes, the planetary atmosphere. Yes. So
now this is why we have a little diffraction lens here. Did everybody got one? Okay, we're going to do an experiment after this. Tell us what this is.
Okay, a spectrum. Yes. Okay, so this is what astronomers really get excited about, and it's all just squiggly lines. I know it's not as beautiful as the other images you've seen. But what happens is if you make a spectrum, and you may have heard the word spectrum, it means a rainbow. So you take light from any object. We do this with galaxies. We do this with stars. If you put it through a spectrograph, it spreads it out into a rainbow. And instead of making an image, you measure very carefully how much light is coming in each color. And that's what the squiggly line is. On the bottom axis, that's actually a measurement of the wavelength or the color of the light. And the squiggly line shows you how much light is coming in each part of that spectrum. And there are basically fingerprints that you can read for every chemical element and molecules. So the water molecule, H2O, there are certain wavelengths of light that we know to look for in the rainbow. And when we see more or less of those colors, we know that water is there. And so this was a very quick, short exposure, just a couple of hours. This is a planet that's about 1,000 light years away. And this planet is very hot. It's about the mass of, it's about twice the mass of Saturn. And not quite as massive as Jupiter. But it's so hot, it's very close to its sun. It goes around once every 3 days. Its year is 3 days. It goes around its star once every 3 days. It's very hot. And so the atmosphere is puffed up. And we were sort of interested to see that we actually see the sign of water vapor. This is not liquid water. This planet is really hot. It's a gas giant planet. But there is water or steam in the atmosphere. And I mean, while that's really cool, I can tell you that in a couple months' time, we're going to start releasing the same sort of measurement, detecting the chemistry of atmospheres around other planets, around other stars. It's going to become commonplace, and we're going to even have atmospheres of Earth-like planets, planets that are about the same size and temperature as the Earth. But this was the first one just to show the spectrograph was working. It works beautifully. So we were actually able to see light directly from the atmosphere of another planet and tell what the atmosphere was like.
So Michele, WASP 96b, is that a pleasant place to live?
No, it'd be really, so it's basically like the planet Jupiter, but it's way inside the orbit of where Mercury is. The cloud tops are thousands of degrees.
So if it's too close to the star, then what do you guys think?
Very close to its star. Yes, that's right. Yeah. But we will start taking these same measurements with planets that are farther out from the star and are more the size of Earth. And I think by the end of the year, we'll be looking for things like carbon dioxide, oxygen, water vapor, methane. All of those things we can detect with the Webb telescope. Okay, and here we've got the SMACS. Yes, the SMACS is the name of the Galaxy Survey. So this is the amount of sky that this is, like on the night sky, is if you take a grain of sand that you can barely see and you hold it at arm's length. That's the amount of sky that this is. And there are some nearby galaxies that are we're seeing them as they were only about 5 billion years ago. Yeah, nearby. Took like 5 billion years to get to us. Those are the brighter white blobs that you see toward the middle. By the way, anything you see that looks like a star with spikes coming out of it, that's a nearby star that got in the way of our image. The reason you get those spikes, and I'm sure there's lots of people in the meeting tonight that can tell you, those are called diffraction spikes. And those are caused by the light bouncing off bits of the telescope. So don't worry about anything that has those spikes on it. But in the very middle of the image, there's sort of a white blobby galaxy. And that's about 5 billion, we see it as it was about 5 billion years ago. But what it's doing, did you notice there's kind of this distortion? There are these weird kind of arcs around it. Those are galaxies that are far away and behind that big galaxy. And this is something that Albert Einstein taught us 100 years ago, that what gravity really is the bending of space itself. Einstein never thought he would see that. He thought this would be entirely theoretical. But our telescopes now are so sensitive that when we look at these galaxies in the foreground, we see that their gravity creates a lens, creates a natural bending of space that both distorts and also focuses the light from more distant galaxies behind them. So this is real. That distortion is not produced by image processing or by a computer. That's actually what you would see on the night sky if your eyes were that sensitive. And all of those weird arcs are galaxies that are close to 13 billion years old. We're seeing them as the light was 13 billion years ago.
Wow.
Now you'll notice, for example, and this is a little bit of it's a little bit touchy, a little bit, some would use the word pedantic, perhaps, if you know that word, maybe a little too much detail. But you'll notice that I don't say it's 13 billion light years away. I'm saying that we see it as it was 13 billion years ago, because since that light was released 13 billion years ago, the universe has expanded. And in fact, those galaxies, well, I mean, we're looking at them that long ago. I'm sure all the stars we're seeing are now burnt out, right? But But, the galaxies, since they released that light toward us, they've expanded away from us. So actually where they are now is much farther away, even than 13 billion light years. So astronomers will often talk about things in terms of the past, how long light has taken to get to us. But that doesn't necessarily mean you can put it back and say, well, it's 13 billion light years away. It's actually farther away now. It was 13 billion light years away when that light was released a long time ago.
Okay, everybody, 13 billion times 6 trillion.
Yeah,
come up
that's
with
how
it.
many miles.
Come on. 6 trillion. Get out your calculator.
Yeah,
Really
this is why we
far.
use scientific notation. You don't want to say this in miles. You want to say it even
Okay.
13 billion light years. I can't visualize a billion. Nobody can. I'm doing well if I can do a dozen.
Wow. So the reddish ones that are slits are
Tiny little
stretched
things. Yeah, those are
out.
very distant galaxies. I mean, so those are still galaxies. They're big.
And
But
look
the
at them
little
all.
red dots are galaxies very far away. Yeah.
All of these things, all of these objects are galaxies. And the ones that are dark red are very far away with a slit there. That means that you can't see it except this white galaxy is enlarging it and stretching it out.
That's
Have
right.
you ever put a hand lens on top of the newspaper and notice how it makes the letters stretch out? Try that. Even the little kids, take a hand lens and go over the newspaper.
Or you can also look through the bottom of a bottle. I mean, you just did that
Through the
curved
bottom of
glass
a
to
bottle,
distort
yeah.
everything. Yeah.
Yeah, it's the same
in some
idea.
cases it focuses them.
You can experiment with that. Do we have time for a question?
Of course. We have time for more than one question, I hope.
All right, everybody think of a question, not 13 billion times 6 trillion, okay?
Okay, maybe not everybody think of a question.
Because
but
we're going to
but
do
what
that
we
for
think.
homework. Yes, sir? Is everything are all these things moving away from us?
Yes. So I mean, we live in the Milky Way galaxy, and the gravity of the galaxy is strong enough to keep it together. So the Milky Way galaxy, all the stars you see in the sky are in our own family galaxy, the Milky Way. Every other galaxy is moving away from us with one exception, and that's kind of a famous one. That's the Andromeda galaxy. So the Andromeda galaxy is a galaxy about the size of the Milky Way coming toward us very quickly because it's close enough that our gravity is going to cause us to merge together. So in the case of galaxies, space is expanding. Every galaxy is getting farther away from every other galaxy. But if galaxies start out close enough together that they're actually falling in faster than the expansion of the universe takes them away, then they'll merge into bigger and bigger galaxies. And so over the course of history, this is how galaxies have grown. Smaller galaxies combine to form bigger ones. But as the universe expands, it gets less and less dense, and there's more space between the galaxies. This will probably happen less commonly. The galaxies will stop growing.
So in the future, we won't be able to see any of those beautiful spirals?
Well, it's sad but true that, I mean, in trillions and trillions and trillions of years, all of the galaxies will be so far apart you won't be able to see another one in the sky.
They're moving away
the thing
from us.
The thing that's really sad to me about that is, I mean, so not only do you not see galaxies, which are beautiful, but there won't be any evidence of the Big Bang. Think about that. That people in many, many, many trillions of years, when you can't see anything else except the local galaxy that we're in, they won't have any evidence the universe is expanding.
Oh. Mark,
Lost knowledge. Yeah.
one more question?
Yes, it's in every direction at once. There's no center to the expansion. The universe is absolutely full of galaxies everywhere. There's nowhere that's empty. There's no, like, a lot of people misrepresent the expansion as an explosion. And when you think about an explosion, you think of everything exploding away from a central point. There's no like sphere of galaxies expanding into empty space. That's not how it works at all. It's more similar to thinking about like a raisin bread. So you make dough and you put raisins in it, and then you let the dough expand. And there are still raisins in the middle of the bread, but all the raisins have gotten farther away from each other. The universe is expanding in every direction at once. There's no preferred direction to the expansion. So wherever you are, you see everything else getting farther away. No matter what raisin you're standing on, as the bread expands, all the other raisins get farther away. And we don't know of any edge to this. So, I mean, in the case of a raisin bread, there's an edge, there's a crust, right? We have never found anything of an indicative of an edge. All we see is a distribution of galaxies, everything expanding in every direction at once. There's no empty center that we're expanding away from.
Wow. We have to get Robert over here. Robert Seegers, could you move up? We're going to do an experiment after Michelle's finished. Who, me? Somebody yell for Robert Seegers, and I think he knows he's expected. But first, are there any more questions for Michelle? Yes, sir.
Yes.
She's got you.
A question, real quick. Will the James Webb Telescope at any time to look at the possible planet that researchers have possibly found around Alpha Centauri A, or is it not in the plans at all?
Oh, absolutely. I think it's in the first year of plans. I mean, so specifically Alpha Centauri Proxima. So Alpha Centauri Proxima is the closest star to us right now. It's a very dim red star, and it has an Earth-sized planet around it. And so the very nearest star to us has an Earth-sized planet. One of the things we're really curious about that is it's one of these planets that's quite close into its star, even though the star is dim. So the planet shouldn't be too hot to have an environment that might have life, but the star has huge solar flares, gigantic ones, much bigger than our sun. We've observed these from Alpha Centauri Proxima. And so one of the questions we have is, can an atmosphere survive close to a star that has these big flares? So one of the big questions Webb will be answering about the Alpha Centauri system is, can these Earth-like planets hold up against really extreme solar weather? If they have really strong magnetic fields, maybe they can. I mean, the magnetic field of our Earth is what has helped us keep our atmosphere, because those charged particles from the sun that blast out at us go around our magnetic field. The magnetic field actually directs them away from our planet. But then there are other planets, like both Venus and Mars, don't have strong magnetic fields. And so when the sun blasts them, it destroys their atmospheres. In the case of Mars, it just blew the atmosphere away. In the case of Venus, it blew away all the light stuff like water. So Venus is left with this heavy carbon dioxide atmosphere with sulfuric acid clouds, because all the light stuff got blown away by the sun. So we've got lots of questions about the Alpha Centauri system. So you bet. I'm sure we're going to be doing a spectrum of Alpha Centauri Proxima b, the name of the planet, I hope this year.
And it's not 13 billion light years away. It's only 4.
Yes, that's right. That's the nearest
Piece
one.
of cake.
Yeah.
Times 6 trillion, Okay.
Four times 6 trillion miles.
Yeah,
that's
right.
not
bad. How fast can we go? Well, the space shuttle went 30,000 miles an hour, and I think New Horizons went 35,000.
Depends on whether you mean humans or not. So, I mean, right now, the fastest spacecraft we have is the Parker Solar Probe. The Parker Solar Probe is orbiting the sun right now. And
how fast can it go?
Sorry?
How fast? You think?
420,000 miles an hour is how fast it's going.
120?
420,000 miles an hour.
Wow, that's great.
That's crazy.
That's really fast.
Because you need to go that fast not to fall into the sun when you're that close to it. So that's the fastest human-made spacecraft so far.
It's at the sun, though. I don't know.
It's orbiting the sun, yeah.
Okay. We are so grateful to have your time. I know you've got a million things to do, and we're going to be seeing you on TV, and we're all going to be on TV.
I'll make it back up there, and and please have me for a longer talk. But Tish invited me just to give you a little preview of the web images. It's nice to see all of you guys.
Thank you so much. Give her a hand. Yay!
Turn the camera around. Let me see everybody again.
Woohoo!
No, that's all right.
We are so grateful. See you again soon.
Good to see you, Tish. Bye.
Bye. We need to move your camera so we can do an experiment. Your camera.
Oh, my camera.
Is that important? We could move the other thing. Okay, while they're doing that, we're going to do an experiment. Ready? Okay. Whoever's near the light switch, get ready to turn them off. Okay. Let me see if I can find us.
Let me,
Get me back to beginning.
okay, so,
Thank you.
you want it
I don't have to be on Zoom anymore. I just need to be back to 1.
You better when you're back to 1, okay.
Yes, please. Robert has a thing called a power supply that will put a charge through a hunk of hydrogen. And that's the fast view, yeah. Let's try the white light first, and then we'll switch off the lights. Oh, thank you so much. You don't mind standing up? That's so nice of you. Thank you. We'll wait for Jeremy to give us a thumbs up. Are you ready over there? Yes, all of your peepholes are warmed up. Don't touch the inside, just the outside. Okay. Robert, could we try a white light first, and then we'll turn the lights off? Okay, try the peepholes on this end lights, please. There's also a set of lights that are front. Yeah, very good. Okay. If you didn't get one, we have some more. No, we need it that way. Thank you. Oh, okay. Robert, see if anybody needs one. Robert, see if anybody doesn't have one. This is a practice, just a practice. Anybody in the back want to try this? People with hands up are going to get a... We do want those back, yes. We're going to start, okay. So one thing that the James Webb Telescope has is a spectrum reader called a spectrometer, and it can tell you what elements it's looking at by looking at the rainbow of the elements. Now, right now, you're just looking at a white light. We were born on the third planet from the sun star, and we are programmed to see these colors, and you should be able to see what? Red, orange, yellow, green, blue, indigo, and violet. Is that correct? Okay, so we can turn that off now before I go blind. Okay. Whew. Okay. The other lights probably won't bother us, but my eyes will come back. Did you know it takes a good 10 minutes for your pupils to get back big again? Anyway, Robert has a sample of hydrogen here. Why would it be good to know if you can see hydrogen? What has hydrogen in it? Water. What else? What's mostly hydrogen and makes a big fusion reaction? Did you say star? Good for you. Stars. Now, a healthy young star shows us this spectrum. Get your people ready. Oh, we're going to have to darken that, aren't we? Darn it. I will.
And when you look through the peephole, you don't want to look right in the middle. You want to look towards the outside.
Look through the peephole at that light. Anyone who doesn't have one? You don't have one? You're sharing? Okay. I would like you to tell me what 2 colors stand out as the boldest colors. Red and greenish bluish. Okay, this is called the spectrum fingerprint for hydrogen. So when we see hydrogen through a spectrum, that's a good sign. The star is young and has lots of fuel. Okay, lights. Wait, can you find the other one without the lights? The lights are coming back on. Thank you. Let's try another one. So he won't burn his fingers off. So what about a dying star? What do you think that would show us? Well, we saw those planetary nebulas that were dying stars and what kind of spectrum they might show. Robert's going to pull out next. As soon as he doesn't think it's too hot. Oh, okay, good job. Don't drop it. Thank you. He's got a sample of an element that would be the sign of a dying star. Can you name a dying star? I'll give you a hint. It's big and red. Betelgeuse, yes, that's one. In the armpit of Orion the Hunter. Yes, very good. It's going to blow up someday soon. But it's 500 light years away, so kids, more math for you. Ready? It's 500 light years away. How far is 1 light year? 6 trillion times 500. So it's pretty far. So let's see what lights, please. Let's see what helium looks like. Helium isn't just for party balloons and making your voice sound funny. It's also the offspring of a star that is burning up and using its fuel. And the fuel's almost gone, and it's showing us this rainbow. Is it the same as hydrogen? No, it's definitely different. What are some bold colors? Just yell them out. A lot of yellow, right, yes. Good for you. If you're noticing bold lines, that's the spectrum fingerprint for helium. So when we see that with the James Webb, we know the star is getting old. Okay, Robert. Now we have one more to try. Do you remember the picture that Michele showed us with the graph and the ups and downs and the dots with an H2O on the top? That is, what's the name of that planet? WASP. Okay. It's WASP B, and it's really far away, but it's very close to its star. You remember the big signature on that was H2O, right? Let's see what that looks like through a spectrometer. Robert's got a molecule of H2O right here. Ready? Okay, go. The people behind you, can you see? Should we turn the camera or anything? We're okay? All right. So is water different than hydrogen or helium? Does it have a distinct bar of color that you can identify? What do you see? There is a lot of red because there's H. And oxygen's in there, so there's some green. Yep, very good, very good. Okay, so you can identify water by using a spectrometer too. Okay, thank you, Robert. Good job. Okay, we are going to collect those at the end, so all you have to do is leave them on your seat or just give them to us. Thank you very much. Now, I'm going to go back to where I was. Hope this works. Yeah, there we go. All right, so let's go. Now somebody else is going to talk to you. Ready? Here we go. As soon as it starts.
The James Webb Space Telescope is the next premier space observatory. It will extend the discoveries of the Hubble Space Telescope and observe the birthplaces of planets, stars, and galaxies. It is named after James Webb, NASA's second administrator and champion of many NASA science missions. At 3 stories high and the size of a tennis court, this will be the largest telescope ever sent into space.
Instead of will,
and 100 times more powerful than Hubble. It is so big it has to fold to fit into the rocket only 5.5 meters wide. And unfold segment by
How
segment.
many of you
once
did
in
the
space.
fold the telescope up activity in the
Webb
other
mirrors
room?
are coated with a super
No,
thin
not too
layer of
popular.
gold
Okay.
that is about 1,000 atoms thick to optimize their reflectivity in the infrared. Webb will launch from French Guiana.
Webb did launch perfectly.
It is launched near the equator, taking advantage of Earth's greater rotation speed there to boost launch performance. Webb will orbit the Sun 1 million miles from Earth at the second Sun-Earth Lagrange point.
And it's
The
there
telescope
now.
will observe infrared light with unprecedented sensitivity. It will see the first galaxies born after the Big Bang over 13.5 billion years ago. Webb's infrared cameras are so sensitive, they must block light from the Sun, Earth, and Moon. The 5-layer sun shield is like having sunblock of SPF 1 million. Webb is an international mission with contributions from the European Space Agency and Canadian Space Agency. Scientists all over the world will be able to use Webb to explore further into
And they're
space
waiting in line right now
and back
for a chance
into
to
time.
use it. Thank you, Goddard Space Flight Center. Good friends. Let's move on.
The James
Shh, don't want that. Okay. This is the liftoff in South America. What was the advantage? The equator is actually going faster than New York, yes. Okay. And it unfolded. How do we talk to Webb? Well, right now it communicates with the Goldstone, California receiver and sends a message to Baltimore, Maryland, and the people at the STSCI computer lab. Talking back and forth. It's important for us to understand the balance of gravity in space. If you park your vehicle here, wait a minute, that's not working. Try this. If you park your vehicle here, it's equally balanced between the sun, the moon, and the earth. And it will stay where you put it, pretty much. It has extra fuel in case it goes off a little bit. Like recently it was smacked in the back by a little asteroid, but it's okay. So it's balanced in a spot that's 1 million miles from the sun. I'm sorry, 1 million miles from the earth, from us. It's in an orbit they call the halo orbit. It goes up and down like this on the backside of the moon. We want to thank the nice people from Corning Glass. Over in Corning, they make all kinds of glass, including the dishes in my kitchen. But many offshoots of Corning exist all over the world. And in New Hampshire, Keene, New Hampshire, there's a factory that makes the mirrors for these beautiful hexagons you see here. And also parts of the imaging instruments. So we are so grateful to Corning for their work. So why should we study infrared light? I would like everyone to just stand up a second and touch your chair where you were just sitting. Get up and feel your chair. Is it warm? Your chair. Not your butt, your chair. All right, now your fingers are infrared sensitive. They're sensors. And if you touch your hair, you can feel the warmest places and the cool places, like the end of your nose. Like your puppy has always got a cold nose. You can tell when something is cold or hot. You're born that way. You've got infrared sensors in your fingers, but our eyes can't see. If I look around the room, I can't tell who's got what temperature. We've been through that with COVID, right? Somebody's always taking your temperature with an infrared something or other. Okay. But studying infrared light turns out to be the best way to go if you're looking into deep space. Here's an example of visible meerkats and infrared meerkats. Freshwater crocodiles, ooh, and infrared crocodiles. Crocodiles aren't very warm. If they were really warm, they'd be white on this infrared picture. Yeah. So the whole spectrum goes kind of like this. Just like you saw the rainbow up here with the white light, we've got a rainbow of different kinds of wavelengths of light, all the way from, whoa, we almost lost one, from gamma rays, which are the teeny tiny ones that could come right through the wall and through us. Not very often, but they do. To X-ray, which, you know, when you go to the doctor and they put that heavy thing on you and you gotta, he leaves the room so he doesn't get bombarded with X-rays. Okay. Then the visible part, which is the rainbow we can see. Then the infrared has a huge number of different wavelengths. Infrared, we found out there's so many kinds. And when you guys grow up, all you students, I'll bet you'll find a new kind of wavelength that we didn't even know existed because they're invisible to our eyes. And if you go all the way to the end, the largest waves of all are the radio waves. And by the way, here at Kopernik, we're going to be talking using radio waves, talking to the space station in a couple of weeks, aren't we, Mr. Desker? And we're going to use the old-fashioned method, which is a radio. But you have a cell phone, don't you? We're using radio all the time, yeah. Okay. All right. You remember the Eagle Nebula, our friend over there? Well, here it is in visible light from the Hubble and infrared light. The Hubble does have a small infrared camera, but the James Webb is almost completely infrared. And here's an infrared light that the Spitzer telescope made. Try a look at this. This is so cool. We're going to move it. Get ready to move. Go. It's going to move, I hope. Just a second. Moving. Oh, there it goes. So we're starting off with the Hubble's optical view of the eagle. Watch and see, just like a puppet. Can you do that? That's an eagle. And it turns into infrared. What's the advantage? You can see right through the clouds, just like Michele said. The firefighters use it all the time. Terrific tool to see deep into space. Now, how do you know if things are coming at you or going away from you? Well, that's where you also see the wavelengths helping you out. Here's an example. If this is you and you see something that looks blue, it's coming toward you. That's a blue shift. If this is you and you see something going away from you, that's a red shift. So when we look at that rainbow, if it's shifted over just a little bit, you can tell if it's coming or going. And like Michele said, most of the objects in space are moving away from us. All right, let's explore the universe. This is a review a little bit, but what are most of the scientists looking at here? Can you read my chart? Most of the scientists want to look at galaxies, right? And the intergalactic medium. Hey, there you go. Awesome. All right. It's because they don't know what's in there. Yes. All right. The other very popular ones, exoplanets and their disks. Wouldn't we love to find another Earth? That would be cool. Now, one of my teachers down at Goddard Space Flight Center taught me this. I want you to think of when you are cleaning under your bed, are there dust bunnies down there? Everybody's got dust bunnies, okay. They stick together if you push on them with the broom. This is how we think the stars form originally, starting with particles of hydrogen, and some of it's molecular hydrogen. And some of them start to stick together. If they get hot enough, they rub against each other, and they become galaxies. And then they become galaxy groups. And then there are universes. And how many universes are there? We don't know, because Michele said in every direction, the same huge numbers of galaxies in all directions. I want to compare the Hubble Deep Field, which is one of my favorites, with the James Webb SMACS Deep Field. Now, I want you to know, though, this is not this, the one on the right is not the same place, but they're both similar photographs. The Hubble's people added a little animation to make it more exciting. Let me pause it right about there. Now, tell me, what's the difference? Webb, Hubble. Which one's got more stuff? Webb's got more stuff. In between everything, there's something else. And if we could zoom in on that, you should practice zooming in on that. That is so much fun, because you just go in and in and in for a long ways. Now, the Hubble people also want you to know it took them about 2 weeks to make and have the shutter open to make the picture on the left. 2 weeks of the camera open and gathering light. But the one on the right was done in 5 hours. So it's an advantage. Mm-hmm. Oh, what's wrong with the Hubble? Well, first of all, it's 30 years old, and it's been repaired a couple of times. And the other reason is it's running out of batteries and the ability to use the gyroscopes to point it at certain things. Some of the parts still work, but not all of them. Now, everything that NASA sends up, we expect it to come back down, except for the James Webb and a few other exceptions. So the Hubble's coming. It's going to come down, yes. But it's going to run out of fuel. The fuel is necessary to keep it lifted, right, in orbit. So we have to watch for it. It's going to aim, they're going to always aim it for the South Pacific. If you're going to Tahiti, bad idea, okay. But you know what I mean. Everything that goes up has to come down eventually, and 30 years is a long time. Don't you think? And so we've been waiting since 2007 for James Webb to be finished. And so it was given more money and more money and more money, and now it's done. Okay. So I think it's a wonderful experiment here to compare, but don't bash poor Hubble. It's been doing a great job, and it blew us away for 30 years, right? We love it. We are just getting started with the James Webb images. We know that every week they told us you'd get 5 more images, so it's almost time. Next Tuesday, maybe we'll get 5 more, if they're ready. Think of the galaxies as a flip book, and the ones that are the closest, you can see the spiral arms, but the ones that are farthest away, see how they seem to dissolve into a glob? They don't have any real structure. And this is the oldest galaxy we've ever seen. And that's about 13.1 billion light years away. That's the last I heard anyway. And we've seen this one and spent a little time with it. This is the Stefan Quintet. We've seen this one, the Carina Nebula. It's so beautiful. I think I want to put that on my desktop. The Southern Ring Nebula. I put this in here because I thought it was cool that it's in the constellation called the Flying Fish. You ever heard of that? It's way down by the South Pole. You have to go down to Tierra del Fuego to see it. I mean, it's way down there. Yes. The picture of the fish. Let me go back. It does. It looks like a paramecium or an amoeba or something. Yeah, maybe it is. Well, we know it's really hot inside, and this James Webb can take the temperature and tell us what elements it's made out of. We'll keep our eyes on it, yeah? That's an interesting observation. Then the last part is we can see the atmosphere of all the planets that we're looking at. And this is the Earth's graph of atmosphere. We're having a little trouble with carbon dioxide right now. A lot of trouble with carbon dioxide. And here's our WASP 96b with its water. Pretty cool. It's nice to know that water is out there. By the way, there is frozen water at the very bottom of the crater that we're going to on the moon. Way down at the bottom of this crater, the sun never shines, and it's about 400 below zero down there. So if you want to put your frozen pizza and cheeseburgers down there, that's where you put it to keep it, from getting spoiled. When you go to the moon, it's going to be a hungry time. You're going to have to eat something. And this is our beautiful SMACS. Yeah, we've spent a little time with that. So I encourage you to go to the website, which is web.nasa.gov. That's easy. web.nasa.gov. We'll show you all about it. And I thought I had a link on this page. Let me see. Nope, I don't. Okay, can you remember that one? All right, what's coming up next is we're going to the moon with Artemis. And there's a young lady from Syracuse that wants to be the first woman on the moon. And I hope that she gets the job. I can't wait to follow that, see what happens. Thank you very much for your time. It's been fun. And enjoy the evening. Do we have any telescope news?
I believe the observatory is open. We're working on getting some globular star clusters.
We're looking at globular star clusters tonight. Do you want to see some stars? All right. Thank you very much. Have a good night. Yay. I'm closing. Can you do this for me?